Hello students, welcome to the class. So we'll continue with our chapter classification of elements and periodicity in properties. Today we will see the theory part 6, in which we will cover the remaining part of the section 3.7. So this is the disclaimer. In this lecture we would be seeing the physical trends and chemical trends as well. So we have already covered some part of it. We will see the rest of the remaining physical trends, and then we will move to the chemical properties. After that, we will compare the reactivity of elements and correlate it with the occurrences in the nature. And lastly, we will try to develop a relationship between ionization enthalpy and metallic character. So these are the topics that we will cover today. In the physical properties, we will see trends about the electron gain enthalpy and the electronegativity. We have already seen the trend in the atomic radius, ionic radius, and the ionization enthalpy. Then we will move on to the periodic trends in the chemical properties. And lastly, we will try to relate the periodic trends with the chemical reactivity. So here is your first physical property which we will discuss today. It is electron gain enthalpy. Now what is electron gain enthalpy? It is the energy that is being utilized when you add electron to a neutral gaseous atom. Right? So the enthalpy change or the energy change associated with that process is called as the electron gain enthalpy. Now this process can be shown with the help of an equation. Here you have your X element which is present in the gaseous state. So this is the most important part, and this is followed for both ionization enthalpy and the electron gain enthalpy. That electron should be removed, or in this case it should be added to a gaseous atom. Now you add electron to the metal or to the non-metal. Suppose we are taking X here, then it will get converted into X minus. Now the enthalpy or the energy change that will occur during this process is called as the electron gain enthalpy. Now energy change can happen in two ways. Either after the reaction there would be a absorption of energy, means the process requires energy to be completed. So in that case we will call it as endothermic, or it can be exothermic also, where after the addition of electron your energy is released. In that case we will represent the energy release with the help of a negative charge. So this is a very important difference between the ionization enthalpy and the electron gain enthalpy. Ionization enthalpy is always positive. We have to always apply energy to remove an electron, whereas in case of electron gain enthalpy it can be both positive or negative. Now it will totally depend upon the electronic configuration, that whether it will be endothermic, that means energy absorbing or positive energy, or exothermic, that is energy releasing or negative energy. Now a very closely related term to electron gain enthalpy is electron affinity. Now students get confused in this terminology. A very simple definition for electron affinity would be that it is simply the negative of the enthalpy that we have taken in the electron gain enthalpy, right? So it can be represented with the help of equation. Suppose delta EGH, okay, delta EGH, that is your electron gain enthalpy, is given by this value. Just take the negative of that, you will get your electron affinity. Okay, so electron affinity is a negative of electron gain enthalpy. Remember, this point is an important one. Now we'll try to discuss the trend and periodic properties. We know now what is your electron gain enthalpy. Now how it varies in a periodic table, this should be addressed. If I talk in general, so this trend of course has some anomaly. We will talk about that. But what are the general trends? It becomes more and more negative across a period, right? It becomes more and more negative as we move from left to right in a period. Whereas the reason behind it is that, when we move from left to right, the size decreases. Now the incoming electron will have to be accepted easily because now the size of the atom is small. Therefore, the distance between the outermost shell and the nucleus is less. Therefore, to add the electron at the outermost shell is easy. Okay, so this is very important, that your electron gain enthalpy becomes more negative because the size of atom is decreasing. And hence, you can easily add electron to a smaller atom. Now, what about the trend that we see in a group? So it becomes less and less negative to add an electron when we move down a group. Why it is happening? Because as we move down the group, the size of the atom is increasing. Therefore, it will be difficult for us to add an electron. Now, all of this is related to the electrostatic force. If you are adding an electron at a distance larger than the previous one, I would say farther from the nucleus, then the electrostatic force of attraction is less because it is inversely proportional to the distance. Therefore, it is difficult to add electron to a larger atom. So we can say that due to the addition of electron farther from the nucleus, it is difficult to add and hence it becomes less negative. Now, what is the reason that if the addition is easier, then it is becoming more negative? If the addition is difficult, it is becoming less negative. How do we understand that? So that is a very important point to discuss now. What I am saying, I am repeating it again. So when it is easier to add an electron, the electron gain enthalpy becomes more negative. When it is difficult to add an electron, the electron gain enthalpy becomes less negative. You know this. But how do we define this? What is the reason behind it? The reason is that if it is easier to give an electron, means your atom must be going to a more stable state. That is the reason it is easily accepting the electron. And always in the more stable state, the energy of the atom will decrease. We have seen it in the structure of atom. Whenever we go to a lower energy state, it is stabilized. So since it is easily accepting electron, means it is getting stabilized, and in getting the stabilization, it is releasing energy, and therefore the electron gain enthalpy is becoming more negative. And the opposite is true in case of less negative one. So how many groups of element have very high negative electron? So we'll see on to that. To illustrate that, we have a table right here. It is table 3.7 from the NCERT. You can see that as we are moving from left to right, so consider it for the lithium. Lithium is having a lesser negative value, -60, then a greater negative value, -141, then again greater negative value, -328, and then again a greater positive value. So this is the exception. We'll talk about this. Just don't take this group 0. So you can see that as we are moving from left to right, we are seeing that the electron gain enthalpy is becoming more and more negative. Okay, it is becoming more and more negative. Whereas if we are moving from up to down, it is becoming less and less negative. So you can see that trend in lithium and sodium. As we move from lithium to sodium, the value has become less negative, from 60 to 53. Okay, and there is a very high negative value on the right hand side. Now in this table, we can see the trend. Now what is the anomaly here that is to be addressed? The first anomaly is the case of your positive electron gain enthalpy. So you are moving from left to right, your electron gain enthalpy should become more and more negative, but for the case of noble gases it is becoming positive, means we have to apply a extra force on it to get the electron into the noble gas. What is the reason behind it? The reason is your complete octet. Since your noble gas has a complete octet, therefore we have to apply energy to give electron to the, say, your noble gas. The second thing that you should notice is that if you look from lithium to oxygen, there is a very small change, -60 -141. Yes, the positive electron gain enthalpy means it is endothermic. Now there is a very important thing here. When you move from lithium to oxygen, you can see that their electron gain enthalpy has a change of -60 to -141. But as you move from oxygen to fluorine, you are seeing a drastic change, -141 to -328. Now this is almost tripled. What is the reason behind it? What is the reason behind it? Why it is happening? Why your fluorine and chlorine are having such a large value of electron gain enthalpy? Although this is according to the trend, but still there is a drastic change. Of course they are halogens, but what is the reason of electronic configuration that is pushing them to get this electron in a much efficient manner, and therefore they are getting much more stabilized? This can be indicated by the negative value, higher negative value. Yes, the correct answer would be they are attending a noble gas configuration upon gaining that electron, and as a result we can see that there is a drastic change in it. So your reason should be what? Your reason should be that your fluorine and chlorine are getting a stable electronic configuration. Now there is a second anomaly with which you should notice here. I have told that as you move from top to bottom, you will see that the energy will become less negative. But in the case of oxygen and sulfur, this is not seen. In the case of fluorine and chlorine also, this is not seen. Now I have put both of this to address again the anomaly. Let us try to understand this. So what you can see in the table, that your oxygen has a electron gain enthalpy of -141, whereas your sulfur has electron gain enthalpy of -200, but it should become less negative. Similarly for the fluorine and chlorine, the energy is becoming more negative. The reason behind it is the small size of oxygen and fluorine. Now if you move on to the further down elements, means if you see the other chalcogens, or you would see the other halogen like your bromine, iodine, you would see that from chlorine to bromine the electron gain enthalpy will follow the normal trend. That means it will become lesser negative. But in the case of oxygen and fluorine, they have a very small size. Okay, I'm again telling it, your oxygen and fluorine have a very small size. Now in that small area, if you add electron, it will experience a very strong repulsion. Due to this, you are getting, I would say, a lesser negative value. Got it? So again I am repeating it. What is the reason behind it? Why are we not seeing a greater negative value for fluorine and oxygen as compared to sulfur and chlorine? Because they are facing difficulty in accepting the electron due to their small size. And as a result, your electron gain enthalpy is less negative for case of oxygen and fluorine than the expected one. I guess this is clear to you all. What I am trying to say here is that due to small size of the oxygen and fluorine, it is difficult to add electron, and as a result we are getting a less negative value for oxygen and fluorine. And therefore our two exceptions for electron gain enthalpy are written here. So this is very important, that your electron gain enthalpy of oxygen is less negative than that of sulfur, and your electron gain enthalpy of fluorine is less negative than that of chlorine due to its small size, and hence we have to face the stronger repulsion to address that. Now moving on to our next physical trend, which is electronegativity. So we have discussed all about the electron gain enthalpy, right? Now what is electronegativity? Now this is not a measurable quantity. What is the meaning of this? So the enthalpy and all that we have seen in the previous time, they are measurable. You are doing an experiment, the energy is released, you are say observing that energy and recording it. Okay, you are recording it, that is a physical process. But your electronegativity is not a measurable quantity. It is being, you would say, it is being calculated using certain formulas. Now that is done by different scientists, and they are termed in different scales. We will not go on to that, what is the formula to calculate that. But the definition of this electronegativity is that it is simply the qualitative measure. See, it is written qualitative, not quantitative. We are not quantifying it or calculating it. We are qualitating it and saying it that it is the qualitative measure of the ability of an atom to accept the electron or attract the shared pair of electron. Got it? So this is called as electronegativity. As I said, it is not a measurable quantity. It cannot be measured by any physical process. Third and the most important point. So this is quite difficult to understand now, but when we will move to the organic part, you will get a clear picture. But for now, I would say that the electronegativity that is being mentioned in the NCERT and elsewhere, that is not constant. Okay, that is measured with reference to the hydrogen. So that is according to the Pauling scale. We will talk about that, and that is with reference to the hydrogen. And electronegativity changes, and it depends on the element to which it is attached. Again, I am repeating it. Electronegativity is not constant. The value which we will see now, that is in respect to the hydrogen, and it changes if it is attached to a different element. But for now, you can take the values that are given in the table that you will see right now. Got it? As I have said, it depends on the element to which it is bounded. Now, a numerous number of scales are developed to calculate the electronegativity, and those are Pauling scale, Mulliken scale, and your Alfred-Rocco scale. So these are the three scales that are used to calculate the electronegativity. We will not go on to that, how do we calculate it, but we will try to remember the relative electronegativity. Means we will be able to quantify, okay, that this element is more electronegative than this, and this element is more electronegative than that. So that should be remembered. Okay, that should be in your mind. You do not need to memorize the actual value. You just have to have a relative idea that which one is more electronegative. With that said, let us look at the trend. First of all, as we move across a period, the electronegativity increases. Means for the metal, we know that the metallic character decreases from left to right. Therefore, for the metals, the electronegativity is low, and for the non-metals, electronegativity is high. As you move down the group, the electronegativity decreases. What is the reason behind it? The reason is your electronegativity varies inversely with the radius. Now, as the size is increasing, you would face more difficulty to add an electron because your electrostatic force of attraction will decrease, and therefore the electron will not be so prominent in attracting the shared pair of electron. See, in the definition also we have seen that electronegativity is what? It is the tendency to attract the shared pair of electron. That means you are considering the element in the combined state. Okay, and that is the reason your electronegativity is never constant. It is always considered with respect to the element to which it is combined. But for now, we will consider the Pauling scale values that are given in the NCERT to compare them. And in the Pauling scale, all of the electronegativity is calculated keeping in mind that they are attached to hydrogen. Now, non-metallic character increases with increasing electronegativity. So this is very, very important to notice. As the metallic character decreases, the electronegativity increases. And as the non-metallic character increases, the electronegativity also increases. Got it? I guess it is clear to all of you that what is the trend and what is the reason behind it. So let us try to summarize all of the periodic trends of elements. So this can be summarized with the help of a diagram which I have taken from the NCERT. Okay, let us see it one by one. Just focus on the arrow. You can see a red one. Okay, so this is saying that your electronegativity increases as we move up the group. Now, I would suggest you to make this diagram by yourself again and again. How it will help? It will help you to remember all of these trends in one picture. Okay, just try to summarize this whole picture in your mind. Got it? What you can see here? That the electronegativity is increasing from down to top, okay? And your atomic radii is decreasing, increasing from top to bottom. Now, what about the ionization enthalpy? It is increasing from bottom to top, and the electron gain enthalpy is also increasing from bottom to top. What about the period? The electron gain enthalpy is increasing from left to right, and the ionization enthalpy is also increasing from left to right. What about the non-metallic character? You can see it increasing from left to right and decreasing from right to left to right. Okay, I guess it is clear to you all. Now, very important point about the electronegativity. There is no anomaly or no exception in the electronegativity. The trend that you are seeing here, that will be followed. Okay, one line that is important to you all. So remember this point. Every time you see electronegativity, you have to follow the normal trend. There is no exception in that. This is the only trend where you will see no exceptions. Got it? If you are moving from left to right, your electronegativity will increase. If you are moving from top to bottom, your electronegativity will decrease, and that is certain. Now we will move on to the periodicity of valence or oxidation state. So in this point, our focus would be in the trend in chemical properties. We have covered all the physical properties. Now we will move on to the chemical properties. The first is the oxidation state or the valence. So if I talk about the valence of representative elements, then how it can be calculated? But it is not absolute. So it can be changed according to the compound. But for now, you can consider this. So what is the meaning of representative elements? We have talked about this. Which block are called as the representative elements? So they are the S and P block. Okay, S and P block are together called as what? They are called as the representative elements or the main group elements. There is a small reminder for you. So there will be a test on 7th of June on motion in a plane. So just attempt this. It will help you to correlate all of the things that you have discussed till now in the physics. And similarly for the chemistry also, there will be a test on 7th, right? So that will be a holiday for all of you and you will get a chance to attempt that. Just open your SATHEE website and there you will get a link for the mock test. It is going live on 7th of the June. So how do we calculate the valency in case of representative elements? There are two ways to do so. First is calculate the number of electrons in the outermost orbital. That can be sometimes considered as the valency. This is the first case. What is the second case? Subtract the total number of electrons from 8 to get the valency. So you can do it in two ways to know the valency of the representative elements. And remember, it is not followed ideally in each and every case. Let us try to understand this with the help of this table. Okay. So what you can see here, you can see that we have valencies related to 1 and 2. Now they are fixed, right? It is fixed for the group 1, 2 and 3. Yes, that will be available on the SATHEE app. So it is fixed for the group 1, 2 and 3, 13. It is taken as 1, 2 and 3. For the 14th also it is fixed, it is 4. But for the 15th group, it can vary. It can be 3rd, or it can be 3, or it can be 5. How? Simply count the number of electrons in the valence shell. That will give you 5. Subtract it from the 8, you will get 3. So these are the two valencies that are possible. Yes, it is important to visit the site. You can also refer the app also. There also you will get the thing. Similarly, for the 16th group, two values are possible. One is 6, that is directly the number of electrons, and second is 8 minus 2, which is 6. Similarly, for the 17th, it is 1 and 7. For the case of 18, it is most time zeros. Okay, it is most time it is taken as 0. But in some cases, it will be 8. We will consider that case in the chemical bonding chapter in the next upcoming sessions. I guess this valence point is clear to you. How do we calculate valency? We know it very well. We have studied about it in the previous classes also. Now, what about the term oxidation state? This term oxidation state is frequently used in place of valence, and it is a much more used one. When you will move on to the upcoming chapter or to a much higher level, then you will see that the valence word will disappear and you will mostly use the term oxidation state. Got it? So let us take the table to understand this. So first of all, we will take two compounds. One is OF2 and second is Na2O. What will be the valency of oxygen and fluorine? In case of OF2, the first question, what will be the oxidation state of sodium and oxygen in the Na2O? We will try to understand this. To understand this, let us first try to arrange these three elements in the order of electronegativity. I have said it earlier, if you are considering a period, then from left to right the electronegativity will increase. So fluorine will be the most electronegative one, then the oxygen, and then your sodium. Now, let us first consider the OF2. We know that fluorine is the most electronegative element. So this is also an important point for you, that fluorine is the most electronegative element. Now there is a question for you, that if your electronegativity increases, I would say decreases down the group and increases across a period, then which is the least electronegative element? Fluorine is the most electronegative, but which is the least one? So this is a question for you. Try it by yourself. Just look at the periodic table, you will get an idea. For remember the trend, there is no anomaly in it. We know that electronegativity decreases down the group. So which is the least electronegative? Look at the bottom element that you got. So if fluorine is the most electronegative, then what we can say, it will have a oxidation state of -1. Why? Because it can get one electron from the oxygen, and as a result it will have oxidation state of -1. Got it? So the correct answer will be what for the least oxidation state? So I'm least electronegative element. So I'm leaving this question to you. We will get back to it in the next class. What happens to the oxygen? Since oxygen is less electronegative, therefore it will have an oxidation state of +2. How are we getting this? Now focus on this part, OF2. So I have said that fluorine will be most electronegative. Oxygen can have two valencies here. It can have 2, or it can have +2, or it can have -2. So these are the two possibilities. Got it? But since your fluorine is more electronegative, therefore the only possible thing for oxygen is to have a oxidation state of +2. Why? Because oxygen is less electronegative than fluorine. Now what about fluorine? The total compound should be what? It should be always neutral. Therefore, to make the compound neutral, each fluorine will have -1 oxidation state, and that will give you a neutral compound. Now if you are not getting this, no problem. When we will read the chapter redox reaction, there you will get a proper idea on how do we calculate the oxidation state. But for now, you should remember this example at least. Okay, and one more example that is related to Na2O. Now what is the oxidation state of sodium here? What will be the oxidation state of sodium here? Any guesses? What is the oxidation state of sodium? Yes, it will be +1. Very good. So it cannot be any other thing other than +1. It will always be +1. But oxygen electronegativity can change, oxidation state can change in some part. But your sodium and fluorine will always have the same electronegativity, which is -1 and +1. So if sodium is having a +1 and there are two sodiums, then what will be the oxidation state of oxygen? It will be -2. Yes, it will be -2. Therefore, we can see that the oxidation state is also a variable one. For the first case, oxygen has oxidation state of -1, and in the second case, it has oxidation state of -2. So it is, in the first case it is +2, second case it is -2. And the reason is to which element it is attached. It describes that the oxidation state of oxygen will change accordingly. If you want to describe this process, how are we getting this oxidation state? Then sodium is losing one electron, therefore it is having oxidation state of +1, whereas oxygen is getting 2 electrons from the two sodiums, and hence it is having a 2 negative charge. So the answer to the least electronegative element is cesium. Okay, your answer should be cesium. We will not count on to francesium, so there is a reason behind it. Remember this. The cesium is the one which has the least electronegativity, and the fluorine has the one which has the highest electronegativity. Now we'll try to understand the periodicity trend, or I would say trend in the oxidation state, with the help of the table. So what I have done, I put up a table in front of you. Here, your compounds are given with respect to the hydrogen. Here you can easily compare the valencies. For the first group, we have lithium, sodium and potassium, right? And their hydrides. So LiH, NaH and KH. So what will be the oxidation state of lithium, sodium and potassium, given that they are less electronegative than hydrogen? What will be the oxidation state of all of these three in the given three compounds, LiH, NaH and KH? So it will be what? It will be +1. Are you getting my point? So here in the group 1, the lithium, sodium and potassium will have oxidation state of +1. Whereas your hydrogens will have oxidation state of what? So I am leaving this question to you. In case of group 1, what will be the oxidation state of hydrogen? Now moving on to the next one, which is second group. In this case, the calcium will have an oxidation state of +2 and the oxidation state of hydrogen will be -1. Similarly, in the previous group 1, the hydrogen will have oxidation state of -1. Why? Because hydrogen is more electronegative than your corresponding elements. Remember, down the group, electronegativity increases. So hydrogen is the one which is present at the highest site. So hydrogen will be more electronegative than lithium, sodium and potassium. So I would expect more answers from you. Then moving on further, if you look at the AlH3, here the aluminium will have oxidation state of, what will be the oxidation state of aluminium? Any guesses? It will be +3, whereas the hydrogen will be in the -1 oxidation state. Now till this point, your hydrogen is having greater electronegativity as compared to aluminium, calcium, lithium and all. But after the group 13, if you see the carbon, nitrogen, oxygen and fluorine, they are more electronegative than hydrogen. Now, what will be the oxidation state of hydrogen in this cases? It will be +1. Yes, for the group 14, 15, 16 and 17, the oxidation state will be +1 because hydrogen is less electronegative as compared to the carbon, nitrogen, oxygen and fluorine. Got it? I guess it is clear to all of you. If I ask you that what is the corresponding oxidation state of carbon, nitrogen and fluorine in this cases, if it is forming hydrides, so what will be the oxidation state of carbon which is present in group 14, or for silicon or for germanium? It will be -4. Yes, it will be -4. For case of nitrogen, what will be the oxidation state? It will be -3. For oxygen, it will be -2. And for the halogen, it will be -1. I guess this is clear to all of you. Similarly, I am leaving this oxide table onto you. You can look on the NCERT table 3.9 and predict the oxidation state of the remaining compounds. Now there is a small change here. You would see that AlH3 has been formed. Means trihydride is formed. But in case of B2H6, there is a dimer. We will not talk deeply on this. We will discuss about this in the main group element. But the point to emphasize here is that your 2BH3 are combining, they are dimerizing. So when two identical groups combine, it is called as dimerizing. If three identical groups combine, that is called as trimerizing and so on. Here, 2BH3 groups dimerize and they create a dimer. Now question arises, why dimerize? The answer of this lies in the complete octet of the boron. Okay. So if you just draw the Lewis structure, you will find that boron, if you write BH3, that boron will be an electron deficient one. So we will talk about this in the upcoming chemical bonding chapter. There you will see that BH3 is an electron deficient. It is not having a complete octet, and due to that reason, it is getting dimerized. Moving on further, let us do a question on it, what we have dealt till now. Using the periodic table, predict the formulas of the compound might be formed by the following pairs of elements: silicon and bromine, aluminium and sulfur. So I am telling you the group of silicon and bromine and aluminium and sulfur. So silicon belongs to group 14. Listen it very carefully. Silicon belongs to group 14. Bromine belongs to group 17. You know it. Aluminium belongs to group 13. And sulfur belongs to group 16. Now what will be the formula? Your time starts now. For the silicon and bromine pair as well as the aluminium and sulfur pair. So sulfur falls in the same group where our oxygen falls. You have 5 more seconds to solve the answer. Okay, your time is up. The correct answer will be SiBr4 and Al2S3. Just exchange the oxidation state. If this is true, then how we have find it? So silicon belongs to group 14, therefore its valency will be 4. We have seen that. This is the only possible valency. If bromine belongs to group 17, 2 possibilities are there. One is 1 and the second is 7. And in that also multiple possibilities are there. +1, -1, +7, -7. But here your bromine will have an oxidation state of what? It will have oxidation state of -1 because bromine is more electronegative. Let us not focus on that. Simply look at the valency. It is 1. So therefore the compound that will be formed will be SiBr4. Now this can be again understood with the help of the table that we have seen. You can see that silicon is exchanging 4 here and your bromine is exchanging 1 here. Therefore it will exchange 1 and 4 with each other to create SiBr4. Moving on to the next part, which is aluminium and sulfur. So aluminium belongs to group 13, so that is a valency of 3. Similarly, sulfur belongs to group 16, so valency of 2. And hence the complete formula would be Al2S3. This can also be again picturized with the help of this table. The aluminium is having a 3 valency. The sulfur here is having a 2 valency. They will exchange to form Al2S3. Now we will move on to a very important topic for all of you. The question is asked and it is the most important topic, I would say. That is anomalous behavior of, I would say, the properties of second period elements. So this is very important. So you don't have to worry about time. I have plenty of it. So first of all, what is this anomalous behavior? It is seen that the first element of the group, all the groups including 1, 2, 13 to 17. Okay? 1, 2, 13, 14, 15, 16 and 17. These groups have a different property for their first element in each and every case. And they display anomalous behavior, chemical behavior, right? For example, we have seen one exception. You know that lithium and beryllium do not form covalent compound, right? All other alkali and alkaline earth metals, they form the ionic compound, whereas lithium and beryllium forms the covalent compound. We have seen this thing. Now, this is a direct consequence of the diagonal relationship. Okay, this is a direct consequence of the diagonal relationship. What is diagonal relationship? It is, you would say, a behavior of lithium is similar to that of magnesium, and the behavior of beryllium is similar to that of aluminium. Now this behavioral pattern, if you look at the table, then it is represented diagonally, means lithium is diagonal to magnesium, and hence they both are having the same property. Remember, this is only true for the first, for the second period. Okay, the first member of the second period. For lithium, beryllium, boron. Therefore, boron is having a similar property with silicon. They both are painted in brown. Beryllium is having a similar property with aluminium. They both are painted with yellow. And lithium will have a similar property to magnesium. So this is called as the diagonal relationship. So I would request all of you to not discuss anything apart from the subject. Now, let us try to understand this, why it is happening. The first reason is that due to the small size. Okay, so due to the small size of the first member of the group, they are showing this anomaly. Second is, since the size is small and the electrons are there, it creates a high charge density area. Now what is this high charge density? Means large amount of charge in a small amount of area, that is creating a high charge density area, and as a result we are seeing an anomaly. Third point, due to their high electronegativity, we know that the electronegativity decreases from top to bottom, therefore the topmost element will have the highest electronegativity. And the fourth point is that your valence orbital, okay, limited valence orbital. We know that boron has only two types of subshells, S and P. Therefore, it can accept a very less amount of electron. So it has a limited valency, and due to this limited valency, we are seeing this anomaly. This is not seen in case of aluminium because it has three subshells, 3s, 3p and 3d. So this is the reason behind the anomaly that we are seeing in the second period elements. Here is a question for you. So I am leaving this question for you. Just try it by yourself. Next, we will move to the periodic trends and chemical reactivity. So how the periodic trends are changed with respect to the chemical reactivity. So first is ionization enthalpy. We know it that it increases from left to right across a period. Means we can easily remove electron from the leftmost part, and it is difficult to remove electron from the rightmost part. Hence, you can say that the group 1 and group 2 are easily reactive because they can easily give the electron. And that single loose electron can result in a stable oxidation state for the case of group 1. Whereas, if you consider the rightmost part, they are having a higher ionization energy, and therefore, they will lose electron very, I would say, in a difficult manner. And this make them less reactive. Second thing that we will see is electron gain enthalpy. This also we have studied that it is difficult to add electron to the starting elements, but it is easier to add electrons to the rightmost element. Therefore, what is the impact on reactivity? That your rightmost element, that is your non-metal, they can easily gain electron, and therefore they are also reactive. So the leftmost are reactive because they can lose electron. The rightmost are reactive because they can gain electron. As a result, they can easily gain electron, and hence they are more reactive. So the extreme parts of the periodic table are reactive due to two different reasons. We can also try to understand it in the terms of metallic character. Your metallic character decreases across a period from left to right. If this is true, that means the metals on the leftmost part are the most metallic one, and it will easily lose electron, therefore they are most reactive. And hence they have a strong tendency to lose electron, making it highly reactive to form cations. So I am trying to summarize the chemical reactivity with different point. So just be with me with every point. Then we will summarize whole of this using all of these 5 characters. The fifth one is non-metallic character. We know it increases from left to right. Therefore, what will be the impact on reactivity? The reactivity will be highest on the extreme right part, because they have a strong tendency to gain electron, and as a result the reactivity is increased due to their complete valence shell. Now what can we conclude from this all of this discussion? We have seen that on the rightmost part the ionization enthalpy is quite less, therefore they can lose electron, therefore their reactivity is high. On the rightmost part they can gain electron easily, therefore the electronegativity is high. But what about the middle part? So I would say that the reactivity is high on extremes. The most reactive are found on the both ends of the periodic table. That means alkali metal are highly reactive, that are present on the left part due to their low ionization enthalpy, and the halogens are highly reactive due to their high electron gain enthalpy, means they can easily gain electron. But there is a very less reactivity in the center, because they neither have the tendency to lose electron that much prominent, neither they have the tendency to gain electron. Got it? But there is an exception. The noble gas has the least reactivity because of the complete octet. So that is a different thing. But you should remember that on the extreme ends the reactivity is very high. Now this can be again understood with the help of oxides. So they can be used as a parameter for discussing the reactivity. Since your extreme elements are more reactive, they easily form oxides on reacting with oxygen. So we have illustrated this reactivity with the help of oxide formation. Now there is a very important point here in the oxides. Questions are asked from here in both your competitive exams and your board exams, that how do you classify the basic oxide, the acidic oxide, the amphoteric and the neutral. The elements on the extreme left are basic, they form the basic oxides, the metal. The elements on the right extreme are acidic, like your chlorine Cl2O7, whereas the element in the center are amphoteric or neutral. Now in the center, two possibilities are there, amphoteric and neutral. Remember, as you are on the left center, so center can also be divided into two parts, like your aluminium and all, so they form the amphoteric oxide, whereas the right center will form the neutral oxide. So you can see that as we are moving from left to right, the basicity is decreasing and the acidity is increasing for the oxides, right? It is, I guess it is clear to all of you. So this is very important to understand. Now what are amphoteric oxide? That can act both as an acid and base, whereas your neutral oxides are those which do not have a property of acid or base, both. So here is a question for you. Show by a chemical reaction with water that N2O is a basic oxide and Cl2O7 is a acidic oxide. So I am leaving this question on to you. Now let us try to summarize all of this as we are lacking of time. So first is what we have learned, that what is electron gain enthalpy? It is the energy released when an electron is added to a neutral gaseous atom. Second is the negative of the electron gain enthalpy is called as the electroaffinity. The third is electron gain enthalpy becomes more negative across a period and less negative as we go down the group. Third is electronegativity is what? It is the measure or the ability to attract a shared pair of electron. Remember, electronegativity is a relative property. The table that you know or the electronegativity value that you know, they are with relation to the hydrogen. Third thing, there is no anomaly in electronegativity and it increases across a period and decreases down a group. Third thing, chemical reactivity is highest on the extremes and least in the center. And third, this is the table that shows you that which is the basic oxide and which is the acidic oxide and which one is amphoteric and which one is neutral. Now, I will end my lecture with some exceptions. Oxygen has a higher electronegative, less negative value for the electron gain enthalpy as compared to the sulfur. So this was the first anomaly. The second anomaly is that electron gain enthalpy of fluorine is less than that of chlorine. The third is that oxygen has a oxidation state of +1. So this is very unique. Fluorine is the only element with which it has a +1 oxidation state. And the fourth point, that your lithium has a different property as compared to rest of the group, and its properties symbolize the properties of magnesium, whereas beryllium has a property similar to aluminium rather than the other parts of the group. So with this, I end my lecture. This was all for today's session. Thank you.